inshallah we'll continue. Hopefully we'll be able to finish up the whole balance by the end of this session. If you remember, guys, last time we spoke about, please turn your cell phone off. We started the balancing and we mentioned that the balance is a very important and process that you have to do it in all machines, either the rotating machine or reciprocating machine. For the rotating machine, we give 3 cases for the static balance. How can I say that this balance or this process of balance is static, not dynamic? What is the sufficient condition to claim that what you are doing is just static, not dynamic? Summation of force equal to 0 means that you are doing the static balance business, okay? What are the methodologies? Give me different methods to achieve the static balance. Yes, go ahead, Khaled.
By adding a mass.
Mass where?
Opposite of the...
The opposite of the mass which causes the unbalance.
Yes.
The second method?
Removing material.
Removing material from the opposite side or from the same side?
From
Opposite side.
Opposite side? Are you sure?
from the same side.
Same side.
The same side of the centrifugal force, the unbalanced masses. What is the third technique?
Pole. Pole.
All?
Yeah.
No, before the all.
2 masses.
2 or 3 masses, such that the resultant of the balancing masses will be acting in the counter direction of the unbalanced force. You end up saying summation of force is equal to a 0. Okay? All these kind of techniques are applied in one single plane, which is the plane of the unbalanced disk. And this disk could be a gear, could be a pulley, could be a sprocket, could be anything. Once you say that I'm gonna add masses in different planes, then you are no longer dealing with the static, it's called the dynamic. And the sufficient condition for the dynamic balance is to have summation of force equal to 0 plus
Submission of moment.
summation of moments equal to equal to 0. I'm going to give you a very simple example for the dynamic balance. Let's assume that this is a rotating disk and this is the source of the unbalance. It's called M, small m, or I can give it big M, it doesn't matter. Okay. As long as your disk or your shaft is rotating, this M will make a centrifugal force which is equal to M omega square A, M omega square R. خلاص? And now, assuming that the scenario of adding the masses or removing the masses or adding the different masses in the same plane is impossible because of the nature of the machine. Like what, guys? I gave you two examples last time where you are not able to make the static balance. Give me the name of the 2 machines where you are unable to make the dynamic balance.
If it was Dr.
At least one example.
Dynamic or static.
Dynamic. You cannot make static, and you must do it in. You must add two planes, extra planes to add up the balancing masses.
If it was maybe close, Doctor, they come to
Okay, I give a name for this machine. Very well known machine.
turbine.
Exactly, the steam turbine. Actually, it's a very huge structure. It's not allowed for you to make any mess inside the casing. So you end up adding the two dummy discs on the right and the left. Okay, and in these 2 dummy discs you add up your balancing masses. So I'm assuming that this is the case of the turbine, and these are the 2 bearings. You may add up the 2 discs in 2 sides, on the same side or 2 opposite sides between the running disc and the bearing, or outside the bearing. So let's deal with this case. I'm assuming that I'm adding the discs. The reason for adding these discs is to be able to add the balancing masses. خلاص? So let's assume that I add some mass here. I'm gonna call it MB1 at a distance called R1. So you will end up having a force here which is MB1 omega square R1. Correct, guys? Okay. For this one, for the other one, let's assume that I added the mass. There is a reason, guys, for drawing this one 3D. خلاص? So you can imagine what will happen in the when it comes to the summation of a moment. Now, guys, I claim that this is MB2, and this MB2 will make a centrifugal force which is MB2 omega square RA R2. خلاص? If you are looking at these three forces from one side, then you are ending up dealing with what? Dealing with the projection, right? So you can claim that if I am looking from this way, the left side view, okay, then I should see. I'm assuming that I catch the picture or the still shot at this exact orientation of the three masses. خلاص? And if you remember, guys, you have the freedom to claim that your mass is starting from any location, but the in-between locations, they are fixed. Yani for example, if I said I'm gonna assume that that omega square R was acting horizontally. In that case, you have to rotate MB1 such that and put it in a location such that the angle between the M and the MB1 is fixed. You got it? Okay. So now forget about this case. I'm gonna deal with the whatever we have in the picture right now. So now we have M capital omega square R, and if you look at this one, usually you have M balance
1.
1 omega square R1, and then you have this one which is M balance 2 omega square RA R2. خلاص? And then you end up saying if this one is in complete balance status, this means that I'm gonna end up drawing a polygon, which at the end, because there are three forces, it will formulate a triangle. صح كده? But when it comes, listen carefully, when it comes to the balancing, I mean the other condition, which is summation of moments, you have to be careful, guys, because in this case, let's assume that I'm taking a moment around any arbitrary location. Let's assume that this is the reference location for the moment. You got my point? Now, guys, before you proceed and think about summation of moments either analytically or graphically, you have to see how can I figure out how can I calculate the moment for each centrifugal force. Yani for example, if I told you the location, the distance, I'm assuming, guys, that this virtual disk is somewhere here, not on the bearing. It's any arbitrary location, not exactly on the bearing. خلاص? So I'm going to claim if this is the reference location, all the distances measured from one side, let's assume the right side is positive, while the other distances measured on the other side is negative. So we should agree upon all of this. خلاص? So you will end up saying, if this mass is MB1, I'm gonna call the distance from MB1 to the reference location L1. Do you agree?
Yes.
And the distance from M capital, I'm not caring about the direction of the force itself. I'm just caring about the location of the disk. And the distance from the disk itself, on which the M capital is acting, has a distance called LA, just L capital, to be consistent with just R without any subscript. R1, we did not say R1, R2, R3, we just said R. So for the consistency, I'm going to claim that this distance is just L without any subscript. Clear? What about the distance from here to there, guys, to the reference plane, this distance?
L2.
What should we call it?
L2.
Perfect. So now, if I ask you to calculate, listen carefully, if I ask you to calculate the moment for any of the forces, you simply say, I learned from at the very early age, that the moment is the multiplication or the product of force times the distance. Clear? Not only this, you have to be careful, guys. This is where your force is acting. This is where the plane of the force is acting. Can you see what I'm doing? Yani imagine that this is your disk, this is the left disk, and this is the reference plane somewhere here. And let's assume that my force is acting somewhere here, right? When I'm asking you what is the direction of the moment, you will simply say, based on the right-hand rule, the moment should be acting perpendicular on the plane in which the force is acting. Again, did you see where the force is acting, guys? MB1.
Yes.
So that plane, listen carefully. That plane is perpendicular to the reference plane. Do you agree?
Yes.
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 But the plane itself is inclined. It's not vertical, it's not horizontal. خلاص كده؟ Now guys, based on the right hand rule, if you need to figure out where is the direction of the moment, usually we are using the right hand rule, where you let your fingers rotate with the direction of the force. يعني imagine guys that I'm facing the board right now. Okay, I have to do it here. Here is your force. And now I'm gonna let my 4 fingers rotate in the plane of the force. Clear?
Yes.
If you let your fingers rotate in the plane of the force, this means that your thumb is perpendicular to what?
To the plane.
Perpendicular to that plane, right?
Yes.
If it's perpendicular to that plane, this means that I'm going to draw a vector in that direction. Clear, guys? So now, we are going to use the expressions of the electrical people. Usually, if you have vector moving in that direction, and another vector moving in this direction, I'm sorry, heading in that direction, usually we are claiming that the vector in this location is lagging. متأخر عنه. Did you hear this expression before?
Yes.
Lead and lag? Okay, perfect. Now guys, let me put it as a reference here so we can figure out what will happen. Assuming that this is our vector v1 and this is another vector v2, then I can claim that the vector v2 with respect to the v1 is in lagging state. Do you agree?
Yes.
Do you agree about this expression? خلاص? What about v1 with respect to v2?
It's leading.
It's leading. Perfect. Okay. Now, getting back to my business, I'm not going to draw anything here because I'm using the slide. Your vector is getting out of that inclined plane in that direction, right? This vector represents what, guys? Represents the moment, which is exactly equal md1 omega square r times the distance
L1.
L1. I'm not caring about the value now, I'm caring about the direction. Now guys, imagine that this is your plane, okay? This is the plane of your force. And we ended up that the vector which will represent, which is heading in the direction of the thumb, should be perpendicular to that plane in that direction. Do you agree? Now guys, imagine that I'm projecting all of this to that wall. This vector, the marker, which represents the moment, how can I express it with respect to the force? Is it in lagging case or leading case?
This is lagging.
Yeah.
Lead.
Listen. See, this is the force, it's already there. It's acting here in that direction,
Okay.
right?
Yeah.
And this is your moment, right? خلاص? So now guys, how can we measure leading and lagging? Usually by rotating in the anti-clockwise direction. خلاص? So if you are rotating in the anti-clockwise direction, starting from the x-axis, يعني imagine guys, this is your m. Sorry, let's try. This is m1, md1. I'm sorry. Omega 1, omega square, r1.
Yes.
خلاص? Which represent the projection of this one on that wall. خلاص? And this one is what? Is mb1 omega square r1 times
One.
L1. Now, how can I figure out which one is lagging and which one is leading? Very simple. Usually you come to this point and you draw your x-axis and rotate in the anti-clockwise direction. Whatever you will meet first, this is the slow one. It's slowing down, which means it's lagging, متأخر. And whatever you meet next, it is called leading. So usually, guys, if I'm looking to this one, to that force, the moment is doing what with respect to the force?
Is lagging.
Is leading.
Lead.
The moment is leading,
You find the
right?
difference.
Leading with how much angle, guys?
The difference between them.
Leading with how much angle? Usually when I show you this one was
90.
was perpendicular.
Yes, 90.
So it's almost either lagging or leading was
90.
90. Is it clear, guys?
Yes.
Now let's move to the other forces. This force is acting in that direction. خلاص? Now, imagine that this is the plane of where the force is acting. خلاص? Now, using the right hand rule, I need to figure out where is the direction of the moment. So what should we do? Okay, forget about the direction. The moment should be always perpendicular to the force. خلاص? But the issue is it lagging or leading? This actually, you decided using the right hand the right hand rule. خلاص. Now guys, this is your imagine that this is your force. MB2 omega square R2. Do you agree about this?
Yes.
Okay. Now, to use the right hand rule, your finger should go with the direction of the fingers of which hand? Because we call it right hand rule. It's not left hand rule, right? So now guys, here you go. I'm rotating my fingers with the vector. Where is my thumb directing at that moment? Inside, right? Okay, imagine that I'm gonna project all of this on the same wall. Now, this one represents what?
The force.
Exactly, MB2 omega square R2. خلاص? And your moment is lagging by 90 degrees, which is equal to MB2 omega square R2 L2. Do you agree, guys?
Yes.
Okay. With the same procedure, can you tell me where is the force, the unbalanced force M capital omega square R, and where is the moment? Okay, give me the conclusion. I show you how to do it. Again, here is the plane. خلاص? Here is the plane. And here is the force, right? Here is the force. Okay, now I need to use the right hand rule to be able to figure out the direction of the moment. Here you go, guys. This is your force, right? This is the plane of the force. خلاص? This is my right hand. I'm gonna let my fingers of my right hand go with the direction of the force, the M capital omega square R. Where is your finger heading? Outside, right? Now imagine that I'm taking everything and projecting on that wall. You will end up having, this is I'm gonna build up everything on the same figure, right, guys? خلاص? So this is what? Omega square R. خلاص? Now tell me, where is your M capital omega square RL?
90 degrees.
This direction or that direction?
The right.
Perfect. Okay. Now I can see also, guys, that M capital omega square RL is lagging the force by 98 degree. Then we can come up with a conclusion. If the arm of the force is positive, didn't we say, guys, that all the lenses on the right side are positive?
Yes.
If the arm of the forces or the arm of each force is positive, this means what? That the moment is always lagging. Allah ينور عليك. Clear? And if you go to the other case, your moment is acting in this direction, right? While the force, I'm speaking here about MB1, guys. The balancing masses, which is on the negative side. Clear? So now you are saying MB1 omega square R1 L1. Clear? So what is the conclusion that I can come up with? As long as the distance or the arm of the force is negative, then I should end up having what? Leading or lagging? Leading moment. خلاص? Now I'm gonna draw everything on this picture. So M omega square, I'm gonna make it dotted. All the forces I'm gonna make it dotted to distinguish between the force and the moment, because I don't have another color. Any marker there, guys? Let me see if I have it here. حد يفتح لنا النور يا شباب. مهم جدا الحته دي ان احنا نفهمها. Okay, there you go. So again, I'm gonna claim that all the red colors are the A, are the forces. This one is force. خلاص? This our force MB1 was somewhere here. It's MB1 omega square R1. خلاص? And then the A,
The moment.
how was the moment? Leading or lagging?
Leading.
Leading. For the negative L, leading. For the positive L is A, lagging. If it's leading, it means what?
Right.
Means I have to draw it A in that direction. Do you agree?
Yes.
خلاص. This what? MB1? Please tell me. MB1 what? Omega square R1
L1.
times L1. خلاص? Now guys, I'm gonna take all the moments out of this picture. Because you will end up drawing two separate figures, one for the forces and one for the A. And we are done with the business of the forces last time. Now, imagine that you are taking MB1 omega 1 R1 and drawing, taking out of that figure and make it in a separate figure. So you'll end up having MB1 omega square R1 times L1. This one is M capital. Omega square R times L. خلاص? This one is, what is the other one? Okay. This one is MB2 omega square R2 L2. L2, I'm sorry. Perfect. Now guys, if I told you, let's assume that you already draw the force diagram. And you end up that the force diagram, I'm going to follow up all these red colors. And I'm assuming that the force is in complete balance. What do I mean by complete balance?
Zero.
Wherever you started from, you should end up at. Yani for example, I'm going to say, using of course the scale and all this business that we did earlier. Okay, this is called, let's call it F1 guys, to make it short, which represent MB1 omega square R1. خلاص? And then, this one is what?
2.
F2. And then I should end up having the big F, which represents the mass itself. You got it, guys? Now, as we mentioned, or as we approved, or as we ended up with, that each moment for each of these force should be making a 90 degree. Do you agree? Okay. So now I'm going to draw these forces, starting with F1. So I'm going to take that F1 and make it 90, rotate it 90 degree, and then draw the scale of the A of the moment, which is different scale. Usually the force scale is each 1 centimeter represent kilogram, meter or centimeter. Remember that we used to remove omega square, guys, because it's common between all the terms. So when it comes to the moment, your scale will be what? Each 1 centimeter represent what? Kilogram, meter square, or centimeter square, or inch square, whatever. Clear? Now guys, I'm going to take all these moments and assuming also that we are in complete A balance from the side of the moment as well. خلاص? Now guys, take F1 and rotate it. I'm going to make it in the blue color to be consistent with what we decided here. Okay, that F1 here, I'm going to draw M1 here, which represent MB1 omega square R1 L1. Clear? Now, what did we say? MB1. How was the moment? The moment was leading. This is why I make 90 degree in that direction. خلاص? But be careful. When it comes to the F2, your F2 is acting where, guys? Down. And the corresponding M, which is M2, is leading or lagging? Lagging, which means that I have to draw that direction. Clear? This is your reference. You are lagging 90 degree. This means that your M2 should be in that direction. Clear?
Yes.
And by default, if you close this one, where is our? Okay. This is F1. We said that the M1 is leading. Okay. This one is M1. This one is M2. Then I should have the F, we will call it just the big M without M1 or M2. It should be what? Leading or lagging in that one?
Lagging also.
Again lagging, which means that it should be drawn where?
Right.
In that direction. Which makes sense. Your M1 plus M2 should be equal to the total M. This is why you have opposite direction. Clear, guys? Okay, but we need to make our life easy. Every time I draw the force diagram and then imagine where is the lagging and where is the leading, this is very big business. I'm going to draw a very tricky issue. Give me your piece of paper, please. خلاص? Imagine, guys, that all these figures, all these M's, M1 here, and the M2 there, and our M is down. This is the paper, piece of paper in my hand. If I decided to rotate it any angle, this will change this arrangement?
No, it's the same.
This will make any change in the lengths?
No.
Yeah, it's just, you are just holding the same piece of paper and you decided to rotate it to whatever you like. Then I'm going to decide to rotate it such that each M will be coincident with its own F. Clear? Which means that I'm going to take M2 and rotate it 90 degrees in the anti-clockwise direction. If you rotate M2 90 degrees in the anti-clockwise direction, this means that your M2 takes the direction of F2. And your M1 will take the direction of F1. No, M1 will not take the direction, it will take the opposite. And it makes sense because actually my L1 was negative. Clear, guys? Exactly. The in-between angles, there is no change. But you take the paper and you rotate it to whatever you like. So which position I like it? I like every M to be coincident or in the same direction or in the same line of action of the same force. Clear, guys? So you'll end up F2 is in the direction of, sorry, M2 becomes in the direction of F2. خلاص? And your M1 will be opposite, right? Which means my F1 is here, my M1 will be there. خلاص? And then you will end up that your, of course, I'm drawing with my free hand. This plane should be a little bit like this, okay? And this is your M. You figure it out, guys? Now, let's come up with another conclusion, which is what? This is the end of the story, by the way. خلاص مش هنعمل حاجة تاني. All the M's are represented in the with the corresponding F's as long as the distance L is اروح انتحر انا.
positive.
اما انا بعمل القصه دي ليه؟ You should come up with the conclusion. Don't you see that your F2
Was the same.
was the same direction with sorry, M2 is in the same direction of F2?
Yes.
Because
And your M is in the same direction of
F.
F, right, guys? By the way, I did a mistake here because this was the resultant, so it should be already acting in the opposite direction. So these two is in the same direction because you are usually are saying F1 plus F2 is equal to total F, right? Okay. So now this is why my M is exactly in the direction of F. While M1 is taking the opposite direction of, and what is the reason for that?
L is minus.
Because the L is minus, or L is negative. That's it, guys. This is the end of the story. So whenever you start the business of the dynamic, first of all, you have two ways to go, of course. Either you list down everything in a table, and usually we start with the table by writing down 1, 2, 3, and then the balance, the mass itself. And then you put M1, M2, M3, R1, R2, R3, right, guys? And then the angle theta, remember? And then you take cosine theta, sine theta, because you decide to go for analytical solution, right? خلاص, I'm going to represent it right now, but I'm just trying to refresh your memory with what we did last time. And we ended up having a column which is M times R times cosine theta, and you sum up all these values, and the other column is M R sine theta, and then you end up with two equations. Remember,
Yeah,
one
also.
of them has cosine and the other one, so you take
Square.
the summation of the squares, so you end up having the cosine square plus sine square. You forgot, guys, what we did last
Yeah.
week.
Yeah.
And then you end up having one, you get rid of the theta, then you should be able to get the MR product. Why I'm not able to get M separately and R separately? Because actually you will end up having the three unknowns, M and the R and the theta, right? So usually we are looking for MR product. Is it good or bad for our case? It's good because it gives us flexibility. You can locate your balancing masses at any R you like, and then
Choose the mass.
you choose the mass. But if I fix it the R, then you have to fix the M. But having the MR product, this is good. Although from mathematical point of view, you end up having the three unknowns.
So that's
And then you decide to make it two unknowns by just coming up of the product. This is mathematically, but practically speaking, this is very good. Because I should be able to control the location, and based on the location, I will be able to choose the mass. Yani for example, if the available masses are very small values,
then the
then what should we do with the R?
increase it.
To increase it. What if the masses are very big values? Then you end up having the small the small r's. Clear or not clear, guys?
Clear.
So the end of the story. You do your business graphically. You start by having the forces, خلاص, and then you move to the moment diagram. Check your L, the distance. Is it positive? I'm gonna represent my M in the same direction with the force. Is it negative? I'm gonna represent it in the opposite. And you end up having the equilibrium condition. That's it, guys. This is the whole story. خلاص? Okay. So I'll get back to the slides. So I should do all this business on the slides, but alhamdulillah it's better to do it on the board. Okay, guys. So I'm not going to go through all these hassles because we know very well how to distinguish between the static and the dynamic. Once you have summation of force and this is enough to do your business, you are no longer dealing with a dynamic force. But if your summation of force is not enough, then you have to add up the summation of moment. And in that case, as we mentioned, you have to start by drawing the force diagram, and then after you finish your force diagram, you should be able to draw the moment diagram. But in some rare cases, we usually would prefer to start with the moment diagram, not with the force diagram, as we will see in the problem solutions. خلاص? So I'm going to skip all of this, guys, because I already explained it in very detailed way. خلاص? And let's go to the problem. I think we solved this one last time, right?
Yes.
Okay. So this is static case, and then let's go for is it dynamic for masses M1, M2, M4, respectively the corresponding radii are R1, R2, R3, respectively, and the angles between successive masses are find the position and the magnitude of balanced mass required if the radius of the What do you think, guys, about this problem?
This is static.
Exactly, static. How did I know it's static or not?
Allocation.
Exactly. First of all, he gave me only the masses, the angular position of the masses. And he never talked about in the statement of the problem how these masses are arranged along the shaft.
And that give us a
Did he
link.
mention L1, L2, L3? He just mentioned M1, M2, M3, and M1, R1, R2, R3. So, the end of the story, this is a static. Okay, let's start with the static. Let's refresh our memory with the static. What should we do, guys? First of all, do you decide to go for graphical or analytical? Okay, let's go for both of them. Start with the analytical. I'm going to list down everything in that table, saying that this is a number, and this is a mass, and this is R, and this is theta, and then this is M, R, cosine, theta, because I'm gonna solve it analytically. If you decide to solve it graphically, I would also prefer to build up that table, but you should end up here. No need to go for MR cosine and MR sine. You got my point? But there is something I have to add up, guys. I have to add this because this one would be used to represent the vectors, right? So it's better to add up that column before you think about MR cosine and MR sine. Clear or not clear, guys?
Clear.
خلاص? Okay, so I'm gonna say MR and then MR cosine and then MR A sine.
يا دكتور
أوكي.
الأوميجا ما في حاجة قصدي في الرسم يعني
Omega is common between all the terms.
بيروح مع بعض.
خلاص؟ Okay, guys, how many masses do we have here plus the balancing mass? I have 4 masses, which causes the unbalance. خلاص? And I have to add only 1 mass to take care of all these unbalancing forces coming from all these masses. By the way, when we spoke about the static, we mentioned that there was only one source for the unbalance, which is single mass, right? You can add up also this case. You have multi masses. Okay, can someone turn on the light there? So you may have multi masses causing the multi unbalance, but at the end you should be able to figure out the resultant of this unbalance, and it will be somewhere here, and then you add the balancing masses in the opposite direction. Clear, guys?
Same concept.
Exactly, exactly. So now, let's do the business. M1, 2, 3, 4, and I have the
Balance.
balance. M1 is how much?
200.
200. So you have to be careful, guys. Don't write down your M without showing me what's your units. This is in kilogram, usually put it between parentheses. R's in terms of meter, so I have to write down M. And of course, this one is in degree. خلاص? And this should be kilogram
Kilometer.
meter, and this should be also kilogram meter, because there is no unit for the cosine and the sine. خلاص? Okay, now the second, fill in all these spaces. 200,
300.
300,
240.
240,
260.
260, and then let's go to the balancing mass. I don't know anything about it, so let's write down M sub B. That's it. خلاص? Now let's start by writing down R1, which is 0.2,
0.15.
0.15,
0.25.
0.25,
0.3.
0.3,
0.2.
and again,
0.2.
yes. Here you go, guys. He already gave you the exact location of the balancing masses. So you have to put it down as it is given. 0.2. خلاص? Now for the theta, it's your decision, but I can figure out the values of the theta from the be careful, guys, because he said the angle between successive masses are. What does it mean?
I have to add.
If you assume that my M1 is a reference for the angle, this means that the theta 1 is how much?
Zero.
Zero. And then you add up the successive angle. When I say successive angle,
0 plus 1.
45 means the angle between M1 and the
Two.
M2. So this is 45.
45 plus 75.
And then between, because we are taking this one as a reference, because usually when you say cosine theta, which is theta? Theta measured from x-axis. And the only mass which is located at the x-axis is M1. So please don't make that mistake, because the people might be in hurry and he may write down 0, 45, 75, 135. Incorrect.
75.
This 75 is between M2 and M3. But what you need is between M3 and
One.
M1, which is used as a reference. Here. Okay, so this should be how much?
120.
120. And then you have the angle between M3 and the M4,
120.
135. So 120 plus 135 will give you 225. 250, 255. Correct again? Am I correct or
Yes.
wrong?
Yes.
Okay. So 2, 5, 8, 5. And then we come to this one and we call it theta A balance. خلاص? So how many unknowns we should look at? This M balance and the theta balance. All what you will do right now, guys, is just to multiply this one by that one. You will end up 200 by 2. It will give you a 40, because this is just MR. خلاص? This one will give you 45. This one will give the quarter of 240 is equal to 60. Okay? And this one is 0.3 times 260 will give you 378. And this one is just 0.2
Balance.
M balance. خلاص? Now guys, Tell me, what is MR cosine theta? It's MR is 40.
It's 40.
Cosine 0 is 1, it's just 40, while this one is a 0, because sine 0 is 0.
Yeah.
So I would prefer to add up very thin line between, because it will. I'm sorry, guys. Anyway, when you do it, it's better to add up some thin line between the, to represent the rows. Okay, so this is 40. I'm sorry, I have to go back. Okay, now give me this one. 45 times cosine, 45 divided by square root of 2. How much? 45 divided by square root of 2. How much, guys?
51.8.
How much?
51.8.
5, 1,
No,
31.
31.
31, I'm sorry.
31.8.
Okay, this is the same, 31.8. Correct, guys? Both cosines, 45 and sine, they are the same. Now, you are speaking about cosine 60 times 1, the angle is 120.
Minus
So,
that.
minus 30,
Yes.
cosine 60 is sine 30, yes, minus 60. How much is this? The sine 120, should be positive. 51.96. Okay, now let's go for the number 4. You multiply 78 by cosine of 255.
The previous one minus 30.
Minus 30, not 60.
30? I'm sorry. Shukran. Okay, this one. 78 cosine 255
Minus 20.80.
minus A?
20.80.
20.
1.8.
Minus, right?
1.8.
80 or 18?
No, 1.8.
When you said 80. 18, not 80. ماشي يلا بينا. The sign minus 75.34. Guys, I need you to judge these values before you proceed. See, this angle 255 is located where? In the third quadrant, which means your sine and cosine should be negative. So this is some clue that you are on the right track. خلاص? But this one is a 120. It's the second quadrant, which means the sine is positive, which makes sense. While this one is negative. خلاص? The very last one is just saying a 0.2 times m balance. I'm gonna just make it simple, just m times what? Cosine. I'm gonna write it down this way. C theta, guys. خلاص?
Theta balance.
Cosine, which means cosine theta. خلاص? The other one is 0.8 m times SA, S capital theta. I think the mathematicians are also using these short letters to represent cosine and sine. The end of the story. You add up this one, summation, and you make it equal to 0. And you add up this one, summation, and then you will end up having 0.2 times m times cosine theta balance is equal to some number. And this is equation number 1. And then you have 0.2 times m times sine theta balance is equal, let's call it this one constant 1 and the constant a. So it could be positive, it could be negative, I don't know what will happen. And then you end up, you know how to deal with these two equations.
Square.
First of all, you square both of them and you add them up, you end up having a m2. If you said 1 square plus 2 square, it should give you c1 square, right guys? Plus c2 square. Am I right or wrong?
Yes.
And then out of these two, you will end up having a 0.2 times m square times cosine theta balance square plus sine a theta balance square is equal to this a constant. This one is equal to, you should be able to get the value of m. And then you take that value of m, let's call it equation number 3. The value of m is given. You take that number 3 and then you substitute back in either 1 or a or 2, and you should be able to.
Find the
And it's
answer.
better to substitute in both. Why?
Check for answer.
No, because actually you may say cosine theta is equal to any number, let's say 0.3.
Cosine inverse.
خلاص? How can I guarantee that this theta is located in the first quadrant or the fourth quadrant? So you have to figure out the quadrant. Figuring out the quadrant, you should have the two values. يعني for example, if your cosine is positive and your sine is positive, this means that you are in a
First.
first. And so on. If your cosine is positive while your sine is negative,
Fourth.
this means that you are in the A.
Fourth.
Exactly, 4 and so on. خلاص? This is the A analytical. How can I represent the graphical? Very simple. What we will do for the graphical is the following, guys. This is your MA, M1 times RA, R1, right? And this is your M2R2. All of these are already written down in the first 4 columns. Remember, guys? So now let's agree upon, if you will solve graphically or analytically, you must do that table. خلاص? But when you decide to proceed with the analytical, you just add up another 2 columns, one for the cosine and one for the
Sine.
for the sine. Clear? Okay, so now what we will do next is to decide. I'm going to say each 1 centimeter on that graph is representing whatever the value, the suitable value, such that you have this A, this vector is represented in the available space. خلاص? Is equal to whatever the number that you decide. That should be in kilogram A meter, right, guys? Am I right or wrong? Right. تعالى بقى. We already have the location and the values for all the M's except the A. The balancing mass. We are just representing the balancing mass somewhere here. By the way, مش معنى انك تمثلها هنا this means that your theta balance will be in the third quadrant. لا. It's just an arbitrary location. خلاص؟ يعني زي ما هنشوف كده surprise the balancing mass is existing where? In the
First quadrant.
in the first quadrant. خلاص؟ But this is incorrect. I will explain. خلاص؟ Now, this is MA 1R1. This is M2R2. This one, of course, this angle is how much? This is the A 120, right? Yeah, this is M3 RA, and then this is MA M4 RA R4. And then to claim that the balancing mass is added up to make it in complete balance, this means that your balancing masses should be acting with a force in the opposite A direction. No, this is incorrect. Listen carefully, guys. What we did so far, M1, F1, F2, F3, F4, خلاص? And then when you say that I'm going to end up having balancing, this means that your force of the balancing mass should be acting here,
Should return.
such that the summation of the vectors is equal to A.
0.
So what am I representing here? Actually, what you are representing here is the opposite of the action of the balancing mass. In another word, don't you see that the same length, the length of that vector and the opposite one are the same? We are speaking about the distance. The only difference will be only in what, guys? Is in the direction. Clear? So usually the textbook is making this hassle. He said, okay, let me figure out where is the total unbalancing mass, which is this, represented by this dotted one. And then I'm going to add the balancing mass in the counter direction. Why should do I why should do this all these steps? Once you reach to this one, you are claiming that your balancing mass is taking everything to 0, which means that I'm going to say, okay, here you go. This is my MB, RA, RB. Clear? You take that number, you take that length, multiply it by the scale, and you make it equal to 0.2m. Remember when we gave our balance equal to 0.2?
Yes.
Then you are able to find the m. But when it comes to the direction, here is your direction, guys. This is my theta balance. While the one represented in the figure, it was not the theta balance, it is the theta of the resultant. Which means this direction is representing theta, of the resultant unbalanced masses.
It's written there also, Doctor, to the left.
Where?
Resultant force.
Yes, exactly. Allah ينور عليك. It is the resultant. But why should go through all these hassles? Make your life easy, man.
نفس الريزلتنت اللي هو
Don't you see that you represented all the forces, and you are claiming that the balancing masses should take all of this to the zero? So all what you need to do is just to represent that one in the opposite direction. Take the lens, find out your mass, and then remember early guys when I showed you how to measure the angle. Usually the angle is measured from the point of the merging out of the vector. You draw an x-axis and then you put your you measure your angle in the opposite direction, in the anti-clockwise direction. خلاص? Which means that my theta balance should be greater than 180 and less than 270, because it must exist in the third quadrant. Clear or not clear? طبعا الحمد لله. Anyway, we are done with the static. Let's go and solve the problem for the How much time left, guys?
40.
40? Okay, can you stop the recording?